several comments. First, this topic is very conceptual. There's not going to be any math to 21.1. It's going to be all conceptual. So, remember, when you're thinking about what you're going to study for your test, as far as multiple choice and stuff, this is where those kinds of problems come from. Okay, from today's lesson, 21-1. We're going to do some more stuff with math later in this chapter. Okay, so the topic is magnets and magnetic fields. Okay, magnets and magnetic fields, the terms you've heard for sure, magnets at least, and field you've heard. We're going to have three major objectives today. First, we're going to predict whether magnets will attract or repel in a given situation, which is very similar to the electric charges we talked about with attracting or repelling each other. Second, we're going to discuss the magnetic field around something called a permanent magnet. And third, we're going to talk about the Earth's magnetic field. Okay, those three things are going to be our three outcomes for today. So again, mainly conceptual, much less math than the other sections. First, we're going to take a look at a term called poles. Poles, and these are same spelling as the word pole, but it's a different type of pole, not a pole like a fireman would slide down. This is a pole as far as the magnet goes. So, the ends of the magnets are called poles. It's a very simple definition. It's not even a definition. It's kind of just Mr. Howell saying something. So it's not like in your book or anything.
Wait, the North Pole like Santa?
We're going to talk about North and South Pole also. Yes, we are. We are indeed. Okay?
But slow down, Speed Racer.
Now, for poles, we want to talk about three main ideas. First, the name of the pole, north and south. There's a derivation or there's a reason for it. So let's take a look. We have like a magnet here. Okay? Magnets are traditionally drawn as rectangles. North and south ends of the magnet. North and south ends. Now, the way a magnet is named as far as this north and south end is whichever end would be attracted to that part of the Earth. For example, if I had a magnet that could spin freely, like a compass, you know what a compass is, right? When people used to navigate, they use a compass and it tells them if they're going north or south. It's a magnet, really. That's all it is.
A compass?
A compass. Compass, same thing.
Sorry.
So that's all right. So the way it would work is like this. Here's a compass right here. Is that better?
Yeah, no.
So this is what it looks like. It's spinning freely on an axis in the middle. There's a north end of it and a south end of it. Traditionally, the north end of it is the part that's colored in. You see this on your GPS also, by the way. These little triangles and stuff. You can use a compass on the GPS.
How does your iPhone, you have an app that's a compass, how does it work?
It's able to sense, A, where you are on the Earth using your GPS, and then there's something in there that can sense the angle at which you're holding it. It's usually called a gyroscope. That's the traditional term. So as you angle it, it changes the angle where you're looking, so it knows where you're looking. Ever use Google Maps on your phone? Or who has an Android phone? Okay, there's a navigation program on there that's amazing. Have you ever used the navigation program? Try it sometime. If you use maps and navigate, it's the best one out there. And what you do is, you actually turn and stuff, and if you're walking, it'll show you turning and stuff in the street. It's really pinpoint to the exact location. And it uses this idea here. Okay? Now anyhow, what I'm getting at is this. The compass, when you're walking around on the Earth, it points north. So the black part here is the north end of the compass. This is the south end. And what happens is this. When you're facing the North Pole, the north tip of the arrow is pointed toward it. That's why it's called north. When you're facing the South Pole, okay, the empty part of this triangle, this white part here, with the S for south, would face the South Pole. So depending on the way you're looking is how it was named north and south. Okay, but again, it's just nomenclature, just some names that were given a long time ago, okay? Yeah? No? Okay. So again, the derivation for the names is the direction the magnet would face when on the Earth. That's where the names came from, okay? Second thing. Just like electric charges, like poles repel, opposites attract. Likes repel, opposites attract. Okay? So I'm not writing everything, obviously, so you guys should write what you think you need to write here. So no different than with magnets. Likes repel and opposites attract. There is one difference, though, between magnets and electric charges. And if you remember electric charges, you could have like a positive charge over here, a negative charge over here, and those would attract each other because they're opposite charges. And each of these charges are independent of one another. This is a positive charge over here, by itself, just hanging out. This is a negative charge by itself. They're not connected at all. Whereas magnets always have two ends to them. This is the idea, north and south. So watch this. Even if I took a knife and was able to cut this magnet in half, it would produce two smaller magnets, which would both have north and south poles now. And it would look like that. Okay? It would cut it in half. This half would now have a north and south pole. This half would now have a north and south pole. So no matter what, magnets always have north and south poles. So the north and south come together. They always come in pairs. Whereas earlier, if you have a positive and negative charge, it just happens to be that way. You could have a positive charge by itself and no negative charge. And that would sit alone by itself, and that's fine. But with magnets, you always have a north and south pole. Always, always, always. If I cut this magnet into 10,000 pieces, every little piece would actually have a north and south pole on it. Okay?
What do you mean they come together?
So like you can't just have a north pole of a magnet. Any magnet has both ends, a north and a south pole. You can't just say like this magnet is north charged. It doesn't work that way. One end of the magnet is north pole, one is the south pole.
Is one like positive?
Same idea, yeah. It's not we're not going to use those terms, but the same idea. It's analogous to that, yeah. Erica, then Helen.
You know how you said it's named after how like the tracking is to the Earth? How are you able to tell like if it's a north one or south one? Like, would you do based on its power to the side, or like do you get what I'm trying to say? Is the entire magnet named north or
No.
Oh, you mean just either pole?
Correct. One end is north charged, one end is south charged in a sense.
Oh, okay.
So that's how a compass works. The north end gets pulled in the direction of the north pole there. Okay, which is a little counterintuitive. We'll talk about that in a minute.
Okay.
But it gets pulled toward the north end, which directs you how to go north.
Okay,
Okay?
I understand. Sorry.
It's all right, Kelly.
What is the name for objects? What is the name for objects that don't have separate poles?
Yes,
If
please.
they were just attracted to one
What do you mean?
Wait,
All magnets are going to have two poles.
No,
on
like it's not a magnet though. Things
Non-magnetic?
That are just attracted. But like, okay, I'm thinking of like the zingers. Those things I have that are like magnets. Like, oh, if you have,
It is.
what about?
Those have poles.
Sweater.
Guys, shut that off and open the window. Open the window at least or something. Let some air in. That's fine.
This is a big deal.
I don't understand if they both have poles, then how are they attracted to each other? If they both have like equal poles, is one more?
You're talking about those little, like, they're called buckyballs, the little circular balls that are magnetic?
They're zingers.
What's this
Yes,
here?
they're the same thing.
Okay.
You throw them up and they go. Like I have, I'll bring them in.
Okay, bring them in and let's talk about them then. Because I don't know how to answer your question without knowing what you're really talking about right
I'm
now.
just saying in general. Things
I know, but we got to keep going. We did this last time. We talked too much. I really don't know what you're asking. Can you bring them in tomorrow?
Yeah.
We'll definitely talk about them. That's fine.
Let me.
Thomas.
I make notes myself. Let me see.
So because on the compass, the north, or the part that they call, the part that you use to find out north is attracted to the North Pole, does that mean it's actually the south part of the
Yes, and that's what I'm talking. No, it's actually the south part of the Earth. Yeah, the Earth is actually, the poles are switched. We'll talk about that in a minute. That's a good point you're making. Hold that thought. Okay, very good. All right, let's go to the second. We're going to talk about something called a permanent magnet. And a permanent magnet is an object made from a material that creates its own magnetic field. A material that creates its own magnetic field. So there are certain materials that have magnetic fields around them already. And there are other ways you can make magnets out of certain materials that are ferromagnetic. Okay, and we'll talk about that in a second. So this is magnets that have their own magnetic field.
Is that like iron? Like
Iron is involved, yes, yes. And that's where ferromagnetic comes from, iron. You know, ferro, iron, right? What's the element iron on the periodic table symbol? Fe, yeah, Fe. We're going to talk about that, where that comes from. So, first, materials that can be made into magnets, because a lot of materials are not magnetic, but they can be made into magnets, are called ferromagnetic. Okay? Are called ferromagnetic. They can be made into iron, made into magnets. Now, they obviously, because of the prefix you see, ferro, we just said, they contain iron. Okay, they contain iron. And as everybody knows, X-Men, right? What's his face? The bad guy? Magneto is, obviously he can control things. He's like a giant magnet. And that's why, if you remember in The Last Stand, right? The Last Stand, the third one, I think it was, when they throw Wolverine at him at the very end and he stops him, it's the idea that he's iron in him. Now, that's obviously, it's not, there's actually iron in the adamantium contains iron. Yes. It's not a real element, it's fake, but in the comics, adamantium has iron in it. Okay?
When you have low iron, because isn't it when you're anemic or something?
Yeah, what is that called? Anemic, right? Low iron count?
Yeah, I have that. What does that mean?
It means you have...
Yeah, I take an iron supplement.
Exactly.
What does that make to your body?
I mean, you said you're always cold, right? That's one of the reasons for sure. Yeah. Traditionally, people that have less iron get cold. I know that one. I don't know what else. I'm not sure. I'm not anemic. I don't know. I've never looked it up. All right. Now, here's the next part that is very misleading. And I guarantee you that if this were one of those, like, you remember when Who Wants to Be a Millionaire was a big show? If that was one of these questions, most people get it wrong. All materials are affected by magnets, even though you don't notice it. So if you took like a magnet, right, and you walked up to this piece of metal right here, the magnet would pick up the piece of metal, right? Because the metal has iron in it. But if you take a magnet and walk up to this chair that's made of plastic, is it going to attract? No, because there's no iron in it. But believe it or not, the magnetic field that's produced around the magnet does affect this. There is like some insignificant pull. But everything is affected by magnets. Just like everything is affected by gravitational fields. Just like everything is affected by electric fields. But it's a matter of, is it significant enough to even consider? Okay? So when we think about this, magnets, yeah, they're not going to pull things that don't have iron in, that aren't metal there. But they do actually have an effect on all materials. Okay, on all materials.
So braces have iron in them?
It has an effect on everything, but you can only see it on some things.
One more time.
Like the gravitational pull, it has an effect on all things, but you can only see it on some.
Yeah, like we talked about this. This pen and this stylus, they attract each other because there's a mass. Whenever there's a mass, there's attraction, gravity. But their attraction is completely insignificant when compared to the attraction that the Earth has on this object. Okay?
Yeah.
All right. Next. The last thing I want to talk about is this. And this is something that's interesting to think about. You okay? Go grab some water, guys.
Wait,
So, the next thing to think about is this. An object that is not magnetic can become magnetic when placed in a magnetic field for long enough. For example, things that were on the Earth that may not have been magnetic, some of them are magnetic now because of the field that the Earth produces around it. But certain things can become magnets easier than others. Okay? Easier than others. So, we have two categories. We have something that's called soft magnetically charged. Soft magnetically charged. And what that means is that it's very easy to make the item or the material into a magnet. Okay? It's very easy to make the material into a magnet. But the minute you remove the electric or the magnetic field rather, it's going to lose its magnetism very quickly. It's going to lose its magnetism. So you can make a magnet out of it very easily, but it's not going to maintain that hold or that pull of magnetism. A magnetically hard material is the opposite. It is very difficult to make a magnet out of it. It has to be in a magnetic field for a long, long period of time, or a very, very strong magnetic field. But once you make a magnet out of a magnetically hard material, it holds its charge very well. So soft materials are easy to make a magnet out of, but they lose their charge.
Wait, hard is easy to make a magnet.
So
Harder to make a magnet.
hard is harder to make a magnet out of, yes.
Okay, good, I got that.
A hard magnetic object is harder to make a magnet out of, but it maintains its magnetic pull. It doesn't like go away. Whereas a soft magnetically charged particle. Thomas.
Is that like when you put like a pin on water in a paper cup and you use it to make a magnet? or it's not like a pin. It's
I've never seen that before.
if you have a paper cup and you have water and you click. I don't know if it's a pin or something else, but it becomes a magnet.
Can you send me like a link to a video and I can watch it just to see? I've never seen that before, that's why. It might be that, yeah. I'll give you an example. For example, ready? The other day, I was working on my iPad. And if you look where I'm pointing right now, under here, I didn't notice it, but somebody goes, there's a paper clip stuck to your iPad. And I was like, what? And this actually produces a magnetic field on it. So the paper clip was stuck here. It got magnetically charged. But the minute I removed the paper clip, right? If I moved it to something else, it wasn't like sticking to it anymore. That's a magnetically soft example. It picked up a charge, and it was inside the field of it, so it stayed on here. But the minute I removed it from the field, it lost its magnetic charge. Okay, that's an example of soft magnetically
An
charged.
example of a hard magnetic.
It depends on industry. I mean anything that you want to make a magnet out of. For example, you know the magnets that you put on your refrigerator?
Yeah.
Those don't lose their magnetism, right? They stay magnetic. Those materials, I do not think they were naturally magnetic. They made magnets out of them. They induced a magnetic field on them to make them magnetic, and those remain magnetic. They are magnetically hard materials. Okay, they don't lose their pull. There was an example or analogy I thought of last class, and I cannot think of it right now, and I'll come back if I can. Okay, I'll go back and record over. All right, third thing. A magnetic field is, simply put, a region in which a magnetic force can be felt. A region in which a magnetic force can be felt.
Did you say this chapter or just the section was going to be only conceptual?
This section. So, let's take a look at what's going on here. So, several things. I would draw a sketch of it. It's not a tough sketch to draw at all, yeah. I would color in where you see the red triangles. Color that in on your paper. And along your contour lines, the field lines, make sure you put the arrows going from the north toward the south. And we'll talk about that. Tristan.
Why is the south ended up at that compass there towards
Because remember, opposites attract. And that's what we're going to talk about, how the earth is actually switched of what it should be. We're going to talk about that. It is a common misconception there. But that's the reason. So that's what I was going to point out right now, actually. So, take a look. The south end of the compass is right here. It's this white part of the compass. The north end is the red part. And notice, when it's near the north end of the magnet, you see that the south end is pulling toward it because opposites attract. So south end of the compass, north end of the magnet, they pull together. But when the compass is moved over here, the north end of the compass gets attracted toward the south end of the magnet. So field lines are always going to be drawn in the direction that a north would face. So you could say, in a sense, it's always drawn toward the South Pole. Okay, again, field lines are drawn in the direction that the north end of a compass would face. Look at the north end of the compass. Right here, at this point, it would face down and right. That's why look at this field line. There's the arrow facing down and right. Then here it's facing like toward the right. See the arrow facing toward the right. Then it's facing like up and right. There's the arrow facing upright. And then here the arrow would continue along this direction. So you can think of this like you thought of with negative and positive charges. Remember, the negative and positive charges went in one direction from one to the other. The same idea applies here. Okay, the field lines are always going to be drawn from north to south. Now, this is what Thomas was mentioning a minute ago, which is a really good point. On Earth, it's a little bit confusing. There's a misconception. Here's what it is. So let's draw a circle for the Earth with a north and a south pole.
Really good picture.
Okay? I know, it's wonderful. So, we've got the Earth here, the north and the south pole of it. If you were using a compass and you wanted to walk toward the North Pole, and you were standing right here, okay, so you're standing there, you want to walk toward the North Pole, the compass would look like this. It would be colored in here, and it would be empty down there, showing that the north end is pointing you toward the North Pole. Okay, and this is what people have done with Boy Scouts, and camping, and sailing, anything that involves direction, you have to use a compass. So, if a person was standing here and they wanted to walk to the North Pole, the north end of the compass would point them that way. But a minute ago, I just said that opposites attract, right? So even though we call this the North Pole, This is called the geographic North Pole, really. So let's put that in parentheses, please. Geographic. And this is called the geographic South Pole. But if we were to talk about what's called the magnetic North and magnetic South, they would switch. Because again, remember, opposites attract. If this is a positive top of the compass here, or not positive, a north end of the compass right here, the north has got to pull toward the south, but it looks like this is north. So this is just telling you that geographically we call this the north. But magnetically, this is called the south magnetic pole. And this is called the north magnetic pole. Okay, because if you think logically about the fact that opposites attract, the north tip of the compass is pointing up, which means that this has got to be south up here, but we call it the south magnetic pole, south magnetic. So all you need to know is that in topography or in geography, you're going to hear north and south pole, it's the top and the bottom, north and south. But in like physics and stuff, when you hear magnetic north, we're actually referring to the bottom of the Earth in this arrangement, this orientation. The magnetic south pole of the Earth in physics is the top of the Earth when it's in this orientation. Okay, so just remember that it switches. And another interesting fact is that some things, sometimes the poles will switch over time. Okay, they'll switch over time. And there is some deviation, but what you want to remember from this is that we have geographic north and south poles, but magnetically they're reversed, they're the opposites. Okay. Let's see. Some other fun facts. First, the magnetic field of the Earth, or the reason for it, is actually unknown. The reason the Earth exhibits a magnetic field is really unknown, but there are speculation as to what. And the common thought, which people think is that the Earth has a lot of iron in it, so that it becomes magnetically charged, is actually not what it is. The real reason and the real idea here for this is that the core of the Earth. So you know how the core, there's several layers of the core? There's the inner core, there's like the outer core, then there's like the mantle, and like the crust and stuff. The inner core is fluid. It's a plasma fluid, and the plasma fluids are charged as ions. It's very hot, yes. And the ions in there are charged. And the difference in the ions and the convection that's going on, which is like the swirling of that plasma, is what is predicted, or what is, not predicted, but what is speculated to be the cause of a magnetic field. It's the actual charged plasma and fluid inside of the Earth that is speculated to be causing the magnetic field, not iron. Okay? It might be like a random trivia one on your test. You should write this stuff, but it's not like something that you're going to be,
But where do you find the crust and the mantle?
The plasma is not magnetic, it's just charged. They're charged ions, which can cause a magnetic field. Where do you find it? You can't really find it. It's inside the Earth. You can't really drill down that deep to get to it.
Wait, so
Yeah, it's not like something you're going to access.
It's charged. How far away are we from it?
Far enough that it would never affect you.
Very far.
Yeah.
wait,
It's not something we're going to get to.
Going back to that,
It's like
the magnetic north from lava, and
There's also another relationship that exists. And the relationship that exists is this. Traditionally, the strength of the magnetic field of a planet is directly related to its rotational rate. For example, a planet that spins on its axis faster has a tendency to have a larger or stronger magnetic field. Okay? For reasons unknown right now, the idea is that if it spins faster on its axis, not revolve around the sun, that doesn't matter. The revolution period does not matter. It's the axis of rotation. The rotation period is what matters. So the faster that planet is spinning on its axis, it has a higher, or the stronger that magnetic field is that it produces. Okay, they are directly related.
Wait, what are directly related?
I know. The axis and
Next. I just said it like 3 times. I can't say it again. Sorry.
Very quickly.
Bacteria. Bacteria actually use magnetic poles. And here's what happens to bacteria. The skeletal structure of some bacteria are actually made of ferromagnetic materials. So they're induced magnets from being on the earth for so long. Bacteria that have been around from like the beginning of the earth's age. And a lot of bacteria that are microscopic, they don't have eyes, they just move on their own. And the way they move is by sensing the magnetic pole of the earth. So for example, anaerobic bacteria, which is a bacteria that does not use oxygen. Oxygen is like a poison to this material or this bacteria. An anaerobic bacteria cannot stay above the surface of water or the surface of the ground for too long because the oxygen will kill it. So sometimes it might come above the surface. It doesn't see sun, it doesn't know where it is, but it starts sensing the fact that it's sensing oxygen. And to get away from it, what it does is it feels the pull from its skeletal system. It's not skeletal, but it's structural, let's say. A structural system that has a magnetic material in it. And it can tell the direction it's moving based on the pull of the Earth's magnetic field. So you know how we see with our eyes and people that are blind see with Braille, right? They use Braille to touch, to see and read. Well, that's the same idea. Bats, bats have very bad eyes. Bats send out sonar. Bats send out these sound waves, these screeches. That's why bats screech. They send out sound waves, and based on the time it takes the sound wave to get back to them, they can actually paint a picture of the material that's there, or the boundaries that are in front of them. So these bacteria, in the same way or in a similar way, they use the magnetic pull that they feel in their body to know which direction they're going in, to know if they need to go deeper into the earth to get back underground to escape the oxygen. So there's a lot of applications of this. There's many, many more, okay? But this is just something you might see in nature. No? Chaz? Yeah. They had a question. Anyway, sorry. That's it for today. So take a look at the homework, please. Okay, take a look at the homework.